So we went from 10 to 25. That was difficult. It took years. From what I heard, it was really the leap of creating a phase interpolator instead of just I don't know how they were doing it before, but the advent of a phase interpolator really gave us the ability to get to 25 gig, but it took forever to get there. And then once we hit 25, 56 came pretty easy. And then 100 also came pretty easy. Relatively speaking, there weren't really any hard road bumps. People were able to advance the bandwidth without much difficulty. But then once we hit 200, it's already been years. And we're not much farther than we were when we began. There's been a lot of conversations, a lot of arguments in a lot of different places. 200G seems to be like a big stumbling block. And it's going to be really interesting to see what gets us to 200 and beyond 200, because there's already people talking about 400.
Hi everyone, it's Judy Warner. Welcome back to this week's Ecosystem Podcast. Today I'm joined by Jason Ellison, who is the Principal Signal Integrity Technologist at Rhode and Schwarz. Jason and I are going to talk about VNAs, particularly as it relates to high-frequency domain standards, and that applies to IEEE, PCIe, USB, and others. He's also going to talk about a really interesting thing, which is how to use a VNA in regards to the time domain. We also talk about Jason's involvement in a couple papers that are going to be presented at DesignCon and how you can tap into those. And also Rhode and Schwarz will have a booth there, and he also invites you to join them there and connect with him. I think you'll really enjoy this interesting conversation with Jason. Now let's jump into our conversation. Hi, Jason. Thanks so much for joining me today. It's a delight to have you on the podcast.
Thanks, Judy. Thanks for having me. It's great to be here.
Well, I'm excited to learn about VNAs today, but before we get going on all that subject matter, why don't you give our listeners a sense of your professional background and interest, and then what exactly you do at Rhode and Schwarz?
Sure. So I was a signal integrity engineer for 15 years in the interconnect industry, designing connectors and cable assemblies from 10 gigabits per second and beyond 100 gigabits per second. And in addition, developing the test fixtures and the automated test technologies for production and laboratory tests. Now, I work for Rhode and Schwarz in the test and measurement division, where they supply a diverse market of support industrial components, research and development, automotive, among other things. And my role is the principal signal integrity technologist, where I develop software and measurement science strategies for signal integrity applications.
Well, we're going to dive in now to an area I know you know a bit about, and I know Rohde, I think you told me, came out with a new VNA, but I thought it'd be great to give our audience a sense of what is the role of a VNA, especially when it relates to the areas you're talking about, like high-speed digital and also or analog high-frequency applications? So why don't you just sort of give us a course in that, and then we'll dig a little bit deeper.
Sure. So VNAs are the device that can do many things. One of the notable things would be to analyze low noise amplifiers, for example, or monitor satellite communications. But in this sense, we're talking about high-speed digital, and it's all S parameters. So the VNA would be gathering S parameters for or of interconnects such as cable assemblies, connectors, or something more like a channel, where it would be a backplane or a chip-to-chip cable assembly. And for the standards bodies, we take those S parameters and compare them to some normative mask. And the mask is just a line, and the S parameters need to either fall above, below, or within these lines. Then there's also some criteria that are single value metrics. So if the S parameters fail the S parameter masks, then there's an integration of the S parameters with some weighting function, and then the result of the integration is the value that you compare against the standard. So we use this because sometimes there's little excursions from the mask, like a little blip. And just because we have this little S parameter or part of the S parameters in a very narrow band failing the mask doesn't mean it doesn't work. So they came up with this integrated solution in PCI Express, like integrated return loss or component contribution integrated crosstalk noise. Those are two examples of that. And then there's also some other single value metrics that are specifically for channels. A good example of that would be channel operating margin in the IEEE, where they take measured S parameters of a channel that include crosstalk and then consider this channel in some technology context like data rate, forward error correction, and some limitations on equalization. And they come up with one single value, which is a signal to noise ratio called COM, or in the case of a reflection, ERL, effective return loss. And the PCI Express has something similar with CSIM, where they do the same thing, but instead of a signal to noise ratio, they come up with a eye height and eye width, and that's what they use for their single value metrics for compliance of the channel.
So all these are really compliance and a way to maybe weed out some of the things that might lead you to believe there is a problem, but they're like in this channel operating measurement. Am I getting that right?
Yeah, absolutely. So it's all in the context of what you're measuring. Some standards will give you the capability to determine if a component is compliant, and that would be more the mask-related ones. And then they also give you some ways to give you a confidence level in the channel itself for like interoperability, and that's where channel operating margin and ERL come in.
Okay, so we've been mostly talking about the high-speed digital and frequency domain. Does a VNA also work within the context of a time domain?
Yes. So VNAs, even though they measure S parameters in the frequency domain in complex number, those S parameters can be converted into the time domain to get more insight into what the interconnect is actually doing. So the most common thing is to look at the impedance profile. So the impedance profile is where you take the reflection terms that the VNAs measured and you convert it to time. That would be like SDD11, S21, whatever. And then if you have some kind of knowledge of what your interconnect is, like what the physical structure is, you can start at the beginning in time t equals 0 of this impedance profile and follow it along as you follow along the path that is at the end of your port on your VNA. And you can determine where your noise sources are, like where your reflection noise sources are in time, and relate that to the physical structure. Where this is used a lot of times is with someone made a structure like a printed circuit board, and they would get it to the lab, make some measurements, and they normally would have some kind of expectation of what this thing should look like before they do the measurement. So they take the measurement, they look at the results, and they say, oh, well, the reflections are too high, so what's going on here? And they would immediately take this into the time domain and try to maybe overlay it with their simulated results or what their expected results are. It could be like a previous revision of the test board or the backplane analog, or maybe a little printed circuit board that's used for a cable assembly. Whatever it is, they'll put that model or that previous measurement on top, and they'll see where it deviates. And so if they find that deviation, a lot of times it's going to be a via or something broken, like a cable assembly, solder joints broken, and they could say, oh, that's their location. But even if you don't have previous knowledge of what's going on, the time domain tools can still be used to help you with your debugging. So say you don't know what it was a first. Yes. Say it was a first rev, or you didn't have the simulation data. Then you could use gating. So in gating, you can take a portion of that time domain signal and remove it, convert it back to the frequency domain and see if it made any changes. So if you have like your via in the previous example where you suspected the via was the problem and you remove it, and then you go back to the frequency domain and you see that the return loss has dropped significantly, then you have some confidence that you found the problem. And then you could do a double check where you isolate only that portion, only the via, and then convert that to the frequency domain. If it looks very high, like the problem area, then you have a very high confidence that you found what you were looking for. So there's that, but it's not limited to just impedance. You could also do this with time domain return loss, or I'm sorry, time domain crosstalk, especially near end crosstalk. This doesn't work for far end. So near end crosstalk behaves similarly to impedance, where all the noise sources line up in time with what they're actually where they're at. And I could put a little demonstration video here to show this, where if you stack the impedance profile on top of the near end crosstalk with two separate diagrams, you can follow along with your impedance profile. And then when you find where the near end crosstalk shows up, you've identified physically where that noise source is. And sometimes it's not so good, because if you hit a source of a resonance, it'll look like a decaying sine wave. And all that end effect, that tail of the sine wave, could start to muddy what is after it. But at least then you've found a resonance source, and that's still valuable.
Which is, half the battle at debug, right? Is knowing even where to start. So
yeah, absolutely.
You don't go into the whack-a-mole.
Yeah,
so
absolutely.
For our audience, I'm going to have Jason show that video here so you can see it. But if you're listening, please, you can go over and check out the podcast on YouTube if you'd like to see it. And for our watchers, you can just follow along and you could at least visually see what he's talking about here. And we may do that in a couple more places. So just wanted to give you a heads up there. Okay, more on that, Jason, or can I continue to ask you questions?
Well, there's just one other topic that you might think, why would I use a VNA for time domain rather than a TDR? And
right,
there's a couple of reasons. The VNA has a very high sensitivity, so you can get down to the single micro ohm, which is related to about 25 1 microvolt, which is related to about 25 micro ohms. So that's definitely an advantage. And let's see. And also VNAs typically have higher bandwidth than their TDR counterpart. So sometimes you can get better spatial resolution with a VNA than you would a TDR.
Yeah, I had no idea that you could do that work with the VNA. So I think that's really interesting. So, Jason, I know when we were talking previous to this recording that you have a couple DesignCon papers coming up, and I thought it'd be interesting to talk about what the papers are that you're presenting and how people may be able to learn more about those.
Yep, there are two papers that I'm helping with. The first one is with Mike Steinberg from MathWorks. He's exploring the role of power planes and ground planes and the vias that connect them to the load, and also the decoupling capacitors, and how this whole ecosystem relates to the power distribution network. It's really a follow-up to his 2022 paper where he looked at common structures in printed circuit boards and came up with eigenmode equations so that engineers can get some intuition on what's happening rather than needing to put their structures into field solvers for everything. And it's a really good paper. I've personally used the results of that 2022 paper very successfully, and it's very nice. And so he's trying to do the same thing now with a power integrity approach. So instead of eigenmode equations for signals with vias, he's looking at it from the power distribution network. Again, trying to come up with some closed form equations where you can see where the variables are And if you make one higher or lower, what's it going to do to your power distribution network? So we just got the data from that one in this morning, and he's post-processing it. So I'm looking forward to seeing what happens there. And the other one is with Chris Domenico. So Chris is exploring how the host compliance board in regards to 200G Ethernet is playing a role. So he looked at this previously, and he saw that the proposed limits for the 200 gigabit per second Ethernet host compliance board were very, very tight. And it was clear that while it was reasonable in terms of the board being, or the structure being realizable, it was questionable after, the first, the fifth, the 10th measurement, how reliable this board would continue to be. So he said, well,
interesting.
Because it's going to take some serious effort with the state of the art to get it there, and maybe, cutting some corners in some places. So instead he thought, well, is there another way we can take a look at this? And one of the approaches he was considering was de-embedding. And this is where, instead of limiting the host compliance board to a very rigid limitation, he instead would back off on that and let the fixture modeling and de-embedding algorithm do some of the work. Not all of the work, but some of the work. And there's already precedent for this, so it's not crazy. We're not adding new measurement science to the whole ecosystem. But what we are instead doing is trying to see, can de-embedding help the Ethernet working groups solve some of their problems? And so far, it looks like it's pretty good, and it'll be interesting to see what the end result of this paper is going to be. And it might solve some other problems that I've heard about cable assembly designers having in the other aspects. I've had some people approach me and say, well, I have these cable assemblies and a lot of different test fixtures I've bought from all these different vendors. And depending on what test fixture I plug in, I get a different result. And sometimes I can have a failure, sometimes they'll pass. And it makes me a little uncomfortable. So de-embedding can help with this in that it would remove the fixture entirely from the measurement, so that you're isolating just the media dependent interface and then also the cable. Also, in terms of the HCB that we just talked about, the host compliance board, it could loosen the electrical requirements, which then perhaps this board can be made more robust, and that would be another benefit. But it's not a free lunch. The working groups are going to have to take a really good look at this de-embedding technology. And IEEE is not only about measuring things in the frequency domain. They're going to have to make sure that the oscilloscope is doing it in a way that they're happy with. So the VNA does the de-embedding portion, the actual removal with matrix math. And usually oscilloscopes right now do it with an inverse FIR filter, which is a little different. Not to say that they couldn't use the same math, but the inverse FIR uses convolution as opposed to this matrix algebra. And that's really what enables the scope to still be real time, is this convolution aspect. So they're going to need to look at this inverse FIR filter to make sure they're happy with it. Can we still use it for receiver testing? I think transmit testing will be okay because PCI Express already does this. But they're going to need to look at it. And they're also going to need to consider where they want to place the new test points if de-embedding comes in. So it'll be an interesting take on what's happening in Ethernet today. And I'm looking forward to it. It already looks great, but I'm really looking forward to the final product.
So you mentioned you're co-authoring that paper with Chris. Is Chris also from MathWorks?
Oh, no, sorry. Chris Domenico, he has his own consulting company, and he's also with Panduit. And I'm not co-authoring. I'm kind of like I'm helping out my colleague here, Curtis Donahue. So Curtis Donahue is a co-author, and he said, hey, we're doing de-embedding. I'd really like it if you can step in and help out. So I'm just kind of consulting here, and it's great. I'm really happy I've gotten the opportunity to do that.
Well, high speed and high frequency, it seems like everybody's talking about compliance boards and how to measure things. And it seems like we get out ahead of our skis, like, oh, let's do this speed, let's do this thing before we have the compliance part or the model all, figured out. And so sometimes I feel like we're chasing our tail. And I'm curious about, in that regard, that, everybody's talking about AI these days, with these increasing speeds and complexities. So, and particularly in your domain of expertise, which is interconnects. So, are you seeing any of that sort of creep into your workflow or your areas of interest where AI may come into play?
So as your first comment, it's actually pretty interesting. People getting ahead of their skis. I mean, I
Yeah.
think for a while, folks kind of had it easy. So we went from 10 to 25. That was difficult. It took years. From what I heard, it was really the leap of creating a phase interpolator instead of just I don't know how they were doing it before, but the advent of a phase interpolator really gave us the ability to get to 25 gig, but it took forever to get there. And then once we hit 25, 56 came pretty easy. And then 100 also came pretty easy. Relatively speaking, there weren't really any hard road bumps. People were able to advance the bandwidth without much difficulty. But then once we hit 200, it's already been years. And we're not much farther than we were when we began. There's been a lot of conversations, a lot of arguments in a lot of different places. 200G seems to be like a big stumbling block. And it's going to be really interesting to see what gets us to 200 and beyond 200, because there's already people talking about 400. And
that's just crazy.
And I think these are some pretty significant challenges now. Challenges are significant. We're playing games with modulation. We're playing physical games with what's available from an interconnect standpoint. But, there's limitations. There's manufacturing limitations in terms of tolerances. Just because you can make something doesn't mean you can make a million of them. And we need to make millions of these things.
Right.
So manufacturing tolerances are going to need to improve, or just something fundamentally needs to change. Like I said, with that phase interpolator, it was another tool that was used to get us over the hump. And I don't know what this next tool is going to be to get us over the hump, but we'll see. I mean, it's going to happen. It'll be really interesting to see how it works. And in terms of AI, we're seeing a lot of opportunities come from AI. There have been tons of new business created both for us and our customers. So specifically, It's been high volumes of cable assemblies with very high port counts. Usual port counts, when started with SFP, it was 8 ports, and then it went to QSFP, it was 32 ports. And now we have OSFP, and we have QSFP DD, 64 ports. Now with whatever these cable assemblies are for AI, they're at 128 or 256 ports. And that is a much larger problem than 64. So just as a frame of reference, when you're at 64 port cable assemblies with a wiring pattern to capture all of the measurements, it's 256 measurements. Not that you always will want to do that, but that's a lot. If you go to 128 ports, you're at 1,024 measurements. And if you go to 256 ports, you're at 4,096 measurements. This is a lot of measurements. You can't expect anyone in a laboratory with a 4-port VNA to make all these measurements. So you need automation. Right. And Rhode Schwarz actually has this really cool software package called ZN-Run that helps with this tremendously. And it combines with a hardware that we have, a switch matrix called the OSP. So we combine the switch matrix with a 4-port VNA. It actually could be with a 24-port VNA, even more, some higher port count. But we combine the switch matrix with the VNA, and we have a calibration routine that's actually pretty fast. So I said before, I made these automated test systems before, and one of the most common ways to calibrate them is you measure every path and you de-embed it. There's other ways to do it, but that's one of the more common for a homemade system. That would take forever if you have 128 ports. It could possibly be prohibitive at these high frequencies, because we're not talking about 56 gig cables here. We're talking about 200 gigabit per second cable assemblies with 128 ports. So it's also at 67 to 80 gigahertz is where the bandwidth is needed. And so we have the ZN Run. It walks you through a calibration structure, and I'll show you a video where this is sped up, and it makes it very easy. It's actually very surprising. And then once we have all the calibration data, it's loaded into the VNA simultaneously, which makes the measurements go very fast. Because I've heard about ZN Run ever since I started, and I only recently got to see exactly how this thing functioned live when I was in Munich last, and it is incredible. And so I was like, oh, no wonder why people buy this thing. And people have. There's been a lot of these AI customers coming to us and saying, oh yeah, we demonstrate ZN Run for OSFP, and they're like, well, can it do our AI testing as well for our cable assemblies? Like, absolutely. And we we just have another configuration for it, and they plug it in and go, and it just rifles through these measurements so fast. So it's really nice that we have this opportunity to we already have something that just takes this difficult problem and makes it easy for engineers. And frankly, the engineers are very happy with it. They come to us.
Right.
They really come to us and say, oh my God, I have all these measurements to make this terrible. I don't know how I'm supposed to do this. And they say, oh, well, how about you give this a shot? Give them, we give them a loaner, and they play with it, and they have been happy. So it's been very exciting on our end to be able to support this business.
So it's interesting in this way that you're actually supporting AI developers. Am I hearing you right? Or you're using AI to give you these real-time measurements?
So
or almost real, maybe not real time, these fast measurements.
We haven't incorporated AI into this yet.
Okay.
There are some conversations happening about what we could do with AI, and there's some precedent on how to use AI in measurement test systems for preventative maintenance. And switch matrix actually is one where you would want to use it, because an electromechanical switch in particular can have a failure, but you can sometimes predict when a switch is going to go based on some artificial intelligence metrics. And so this could potentially be a new part of ZN Run in the future. Currently, it's not supported, but it is there is precedent for using artificial intelligence in measurement equipment.
It's really interesting to watch the places that AI is seeping into and sort of becoming an enabler, as much as it can be scary on one hand and exciting on the other. Okay, well, my last question for you, Jason, would be, just as you, as an engineer and sort of someone that has his eyes on the signal integrity focused area, in regards to interconnects, what are some things that just you find really exciting and interesting personally right now, inside the context of your work, or things that you're watching?
Well, first of all, it's the expanding playing field. We see some new players coming out. Luxshare is one in particular that it's interesting to see how that plays out. Of course, there's also some really interesting stuff coming out of Molex that I'm really excited to see at DesignCon. I want to check out what they've got going on. So there's a lot of new things brewing. I'm also interested to see what Amphenol and, again, Luxshare and Samtec come out with in terms of their twin axial cable. So there's been kind of like a twin axial cable arms race to
Interesting.
Yeah, in my opinion, because they all have some really great ideas on how to do this cable, and I feel like it's really setting those three companies apart from everyone else. So we'll see how that goes. I'm interested in seeing how things are getting smaller. We know that there's interconnects that are being placed right on the package. And I'm interested in seeing where that's going to go. If we have standardization, which, back before I started, when I got into as a young man, we're talking about the connector wars, how there was no standardization and everyone did their own thing,
Right.
and it was really rough. And I've had to step away from the interconnect community for a year now, but when I was there, I wasn't personally involved in any of the standardization on these interconnects that are going right on the package. So really interested to see how that plays out. If we get some new SFFs that describe the standardization on the chip to chip and the on chip copper, and also I'm sure there's going to be something with on chip optical, and that to me is also very interesting. I don't know how that's going to play out. I don't know if we have a optical supplier that can provide the millions of interconnects that we need, because optical is traditionally a slow moving entity when it comes to production manufacturing. So we'll see. All these things they're very interesting, and it's all kind of blowing up at the same time, which is wild.
Yeah. It's kind of interesting. You think that these companies have been working in parallel behind the scenes, and they all come out, and it's like, seems like a magic trick when they all come out at the same time. Now, Rohde is always at DesignCon. So you will be at DesignCon, right, Jason? Personally?
Yes. So
Okay.
I'll be there. We have a cool demo at a Genius booth where we hopefully we can have some people interact with our DUTs and our VNAs and the software package that we're showing. And also we have just another demonstration showing a high frequency interconnect with our VNAs. Both should be pretty interesting to those in the digital design space.
Well, Jason, this has been a really interesting conversation, and I know we're about out of time, but before I let you go, can you tell me a little bit more about where our listeners can maybe see some of the things you're talking about if they are attending DesignCon? So give us an idea of where they can find you, maybe at DesignCon or online, and then where you'll be up to while you're at DesignCon, and hopefully I'll get to see you while you're there.
So we'll be at booth 949, and we have 2 high-speed digital demonstrations. One will be just something showing our high-frequency VNAs with a interesting interconnect. And another one will be a hands-on demonstration at our booth in the Genius Challenge session, where you'll be able to use some of our software that hasn't been released yet to test a multi-port interconnect. So I think our audience would be very interested, and anyone that would like to chat with me about signal integrity can find me at the booth or at the various sessions related to power and signal integrity.
Okay, very good. Well, again, Jason, thanks so much, and thanks to you and to Rohde for coming on and catching us up and teaching us about VNAs and all the great stuff you're working on. I will make sure and put all that stuff in the show notes for our listeners. So, and if you're going to DesignCon, make sure you look up Rohde and some of the things Jason has discussed. I will also be there. So come say hello if you're there, and we will see you next week on the podcast. Until then, remember to always stay connected to the ecosystem.